Alright, this is part 2 of investigation 2 for 8th grade. So we left off at doing some Pythagorean Theorem with our right triangles. And now we're going to talk about, so far we've been getting whole numbers for answers. And this says right here, 3 whole numbers that can be the side lengths of a right triangle are called Pythagorean triples. And just some examples of that right here. Our last number, that would be our hypotenuse. Remember, that's the longest side. And the first 2 numbers are the legs that make up that right angle. So we've already seen the first 2 actually. 3 to the second plus 4 to the second gives you 5 to the second. So these are actually just triples that work for right triangles. So these would be side lengths here. And the cool thing about that is if you take any of the multiples of these are very common triples right here. Like for instance, if we took our 3, 4, and 5 and just multiplied each one by 2, 6, 8, and 10, we can see right here that it would still work out. So there are a lot of possibilities with these, and actually an infinite amount of possibilities with these. So I'm very familiar with these first 3 right here because I've been dealing with them quite a bit. And by the end of your high school career, you'll probably have them memorized too. So if you see a side of 3 and 4, you're going to automatically know the last side has to be a 5. Or if you have a 5 and a 13, you'll just remember that the other one has to be a 12. So that'll be nice. So we can actually use that in our theorem here to figure out if these 3 numbers are going to make up a triple for us. So remember, the longest side has to be our hypotenuse, and then 2 and 3 have to be our legs. So what we're going to do then is we're going to take 2 squared plus 3 squared, and we'll get our answer. So we'll get 4 plus 9. And if we add those together, we'll get 13. So we're going to have to see if we add, or no, so we'll check our 4 now. 4 squared would be our hypotenuse, which is 16. And 4 plus 9 is 13, which is not equal to 16, so we would just write this. 13 is not equal to 16. And we can see that this wouldn't work out because our 2 legs squared don't add up to our last side squared. So no, this would be a no here. They are not triples. No. Alright. Alright, once again I have some things highlighted here. This, I already brought it up, this theorem only applies to right triangles and only to right triangles. And all of this stuff in here I'm going to try to sum up for you because it sounds it gets wordy and it sounds very confusing. But if we take the converse of this theorem, which is actually just the backwards version of it, we get, excuse me, we get something like this. It says, if the sum of the squares of 2 sides of a triangle equals the square of the 3rd side, then the triangle is a right triangle. Basically what I'm going to do is I'm going to show you an example of this so that it's not as confusing. So we're going to use the converse of the theorem to determine if something's a right triangle. Basically it's what we just did. Let's say we have a triangle here and we think it might be a right triangle, but we're not really sure. We can actually determine that by the sides. So basically that theorem, the converse says you can take your sides, and if they follow the Pythagorean theorem, then you have a right triangle. So we're going to check that. These would be our 2 legs, 7 and 7. So we're going to square those. Remember our theorem, a squared plus b squared equals c squared. So this would be our a or b. This would be our c, essentially. And we're going to check and see if it follows this. So this would be a 7 squared plus a 7 squared. And we're going to see if that equals our c squared, which is 10 squared. So 7 squared is 49. We get 49 plus 49, so we have 2 7s. And then 10 squared is 100, 10 times 10. And clearly we can see right away we're not going to get 100 on this side. We're going to get 49 plus 49, which is 98. And we know that that is not equal to 100. So, is this a right triangle? No, it is not a right triangle. So we can use the sides to determine whether or not we have a right triangle or not. That's basically what the opposite or the backwards version of that theorem says. So we'll be doing that tomorrow as well. And another couple things highlighted here. So we've had some right triangles that have had 3 sides with lengths that can be expressed as whole numbers, except for one problem that we're going to run into is that most of the triangles that we deal with in this world or in the class, one side won't be a whole number. We're actually going to get some of our irrational numbers. So what we're going to do is we're going to take a look at the diagonal of a square here, right here. So I have a square that's 1 inch by 1 inch long, and if we were to figure out what this diagonal is going to be, we're going to end up getting an irrational number, and I'm going to show you what that would be like. So remember, our 2 legs make up the right angle here, so this would be A and B. And you can interchange A and B all you want. The real important one is what C is. C always has to be the opposite of your right angle. So if we put it into our equation here, a squared plus b squared equals c squared, we'll take our a and b, which are both 1, since we have a square. So that's 1 squared plus 1 squared equals c squared. So we're going to do 1 squared, which is 1 times 1, or 1. We're going to get that twice. That equals c squared. 1 plus 1 is 2. Now remember, when we got to that point, we would always take the square root, because that's the inverse of squaring, or the opposite. So what we would do is take the square root on each side. And I'm going to write the answer up here, but we'd actually get the square root of 2 equals c. So that's what we would leave it as, because we can't do the square root of 2 without a calculator. And even a calculator would be an approximation, it wouldn't be an exact answer. So we would say square root of 2 inches would be this length right here. Alright, I'm going to check to see if my time's up yet. No, we're doing good. So, I think we have one more example like this, and then we're going to work on this tomorrow in class with a bunch of examples. So, it'll be another irrational number. Remember, those are those weird ones, like when we get square root of 2, we can't come up with that off the top of our heads. That's because we get a repeated decimal, but it doesn't repeat in a way that we have a pattern. So it's all those really weird square roots or cubed roots or whatever that we can't figure out. And we will always get square roots with the Pythagorean Theorem because we're dealing with to the second power all the time. So here is one last example for us. It says to find the missing side length, and in parentheses it says we will get an irrational answer. We have talked about those before, and I was just talking about them a little bit ago. First of all, same thing we have to do with all these is figure out what sides are which. Well, they give us that we're looking for B here, so we're trying to find B. The one that makes a right angle with it is 1, so that has to be our A. And opposite our right angle is 2. That has to be our C. So we'll write down our equation here. A squared plus B squared equals C squared. And we'll write down our A, which is 1 to the second. We're looking for B, and C was 2, so C squared would be 2 squared. Alright, so first thing we're going to do is square both of those numbers that we do have. We have 1 squared, or 1 times 1, which is 1, plus B squared. And then 2 squared, 2 times 2, should get 4. And remember, now we're trying to get B squared alone. Okay, so we're going to square that, and we want to get that by itself. So first question we're going to ask ourselves is 1 plus what gives us 4? Well, we know that that's 3. So we know that B squared has to be 3. Same thing could have been found the previous way I did it, where we would subtract 1 from both sides. So we'd subtract 1 over here, it would cancel out with this one, but we would also have to subtract 1 from the other side to keep the equation balanced and that's where we would get that 3 from. So now remember, when we get to this point, something squared equals a number. We always take the square root. That's our opposite property, or our inverse as we like to call it. So then we're left with 1b equals the square root of 3. So b would be the square root of 3 in that problem. And I believe that is our last example. Yes, it is. So we're going to carry on with a bunch of clicker examples tomorrow and some stuff from the book, and we'll go through some more of that together.